Hey, what's going on, everyone? Welcome back to the channel. If you're sitting here right now prepping for the SnowPro core certification, the COF-C03 exam, then honestly, you are exactly where you need to be. Because today, we are doing something a little different. We're not just throwing facts at you. We're going to walk through 10 real exam-style questions together. The kind of questions that actually show up on this test, and I'm going to talk you through them just like I would if we were sitting next to each other, coffee in hand, going through practice questions before exam day. Now, here's the deal. I'm going to read out each question first, along with every single answer option. And I want you to actually pause the video right there. I mean it. Don't just keep scrolling along with me. Pause it, think about it, maybe even say your answer out loud or jot it down. Because the real learning, the stuff that actually sticks in your brain on exam day, that happens when you struggle with it for a few seconds before I give you the answer. So resist the urge to peek ahead. Once we've gone through all the options, that's when I'll come back and we'll break down the right answer together, piece by piece, so you actually understand the why behind it, not just memorize it. And trust me, these aren't your basic surface level questions either. We've got some scenario-based ones in here, the kind with actual SQL scripts and diagrams built into them, because that's exactly the level of complexity you're going to see on the real COF-C03 exam in 2026. So if you're ready, let's not waste any more time. Let's jump straight into question number one. All right, here's question one, and it's about replication groups. Listen carefully. Which statement about modifying replication groups is correct? Here are your four options. Option A, objects cannot be added later. Option B, replication groups convert to failover groups. Option C, replication groups cannot be modified. Option D, schedules cannot be adjusted. Okay, go ahead, pause it if you need to. Think it through. Which one of these is actually true about replication groups in Snowflake? All right, welcome back. Welcome back. This is a question that trips up a lot of people, and I totally get why. The correct answer here is option C. Replication groups cannot be modified. But wait, hang on, because this part's super important and it might sound a little confusing at first. Let me explain exactly what's going on. So here's the thing. When the question says replication groups cannot be modified, it's talking specifically about one thing: converting the group type. You cannot take a replication group and turn it into a failover group or vice versa. That conversion path simply doesn't exist in Snowflake. If you need that kind of change, you have to recreate the group from scratch. That's the actual limitation being tested here. Now, you might be wondering, okay, but can I add or remove databases from my replication group? Can I change the refresh schedule? And the answer is yes, absolutely. You can do both of those things. So that immediately tells us why option A is wrong. Objects absolutely can be added or removed after the group is created. And it tells us why option D is wrong too, because schedules can absolutely be adjusted to control how often that data refreshes. So those flexible parts, the day-to-day operational stuff, totally adjustable. And option B, the idea that replication groups convert into failover groups, nope, that's just not how Snowflake works. These are two separate, distinct constructs with their own purpose. And Snowflake keeps a clear wall between them. You don't get to flip a switch and turn one into the other. So what does this really mean for you? Especially if you're an architect or you're managing a multi-region Snowflake deployment. It means when you're designing your disaster recovery or your data sharing strategy, you need to decide up front, am I building this for replication or am I building this for failover? Because if you pick wrong and later realize you actually needed the other type, you're not modifying your way out of that, you're rebuilding it. That's a real operational cost, and that's exactly why Snowflake tests this concept. They want to know that you understand the design implications, not just the syntax. Okay, let's keep the momentum going. Question number two, and this one shifts us into architecture, which, by the way, is one of my favorite topics because once it clicks, so much of Snowflake just makes sense. Here's the question. Which component enables Snowflake to scale compute without moving data? Your options: A, centralized storage, B, local node storage, C, client-side caching, D, manual partitioning. Take a second. Think about how Snowflake's architecture is actually built. What's the piece that lets you spin up a giant warehouse or a tiny one without ever having to copy your data around? Okay, let's talk about it. The answer here is A, centralized storage. And honestly, this is one of the most foundational ideas in the entire Snowflake platform. Let's break that down together because if you really get this concept, so many other exam questions are going to start making a lot more sense too. So picture this. In a traditional database system, your compute and your storage are kind of glued together. If you want more power, you often have to deal with moving data around, replicating it, syncing it. It's messy. But Snowflake said, hey, let's separate these two things completely. All of your actual data lives in one centralized storage layer sitting in cloud object storage. And then separately, you've got these virtual warehouses, which are just independent clusters of compute power. Now, here's the cool part. Because all of that data lives in one shared storage layer, any warehouse, whether it's an extra small or a 4x large, can reach out and read that same data without needing its own private copy. There's no syncing, no replication, no waiting around for data to move. You just spin up a warehouse, point it at the data, and you're good to go. That's what gives Snowflake that elastic, on-demand feeling. You can scale a warehouse up for a heavy workload and scale it right back down 5 minutes later, and the data never moved an inch. So let's quickly knock out why the other options don't work. Local node storage. That's temporary. It's tied directly to the compute node itself, so it can't be the answer because it doesn't support independent scaling at all. Client-side caching. Sure, that might cut down on some network chatter, but the client isn't executing your queries, so it has nothing to do with compute scaling. And manual partitioning. This one's interesting because a lot of people coming from traditional database backgrounds assume you need to manually partition your tables for performance. But Snowflake handles that automatically behind the scenes. You're not required to define partitions yourself. So what does this really mean for you on exam day? Whenever you see a question about elasticity, about scaling compute up or down, about multiple teams hitting the same data without stepping on each other's toes, your brain should immediately go to this one principle: centralized storage, separate compute. That's the engine behind basically everything Snowflake does well. All right, let's move on to question 3. And this one's a little more practical, a little more hands-on. It's about Kafka. Here's the scenario. A team wants Snowflake to automatically create tables and pipes for Kafka ingestion with minimal setup. Which mode should they use? Option A, default pipe mode. Option B, external stage mode. Option C, manual copy mode. Option D, user-defined pipe mode. All right, think about it for a second. The keyword here is minimal setup and automatically create. Which of these options matches that description? Okay, so the answer is A, default pipe mode. And honestly, once you see the keywords in the question, this one becomes a lot more straightforward. But let's still walk through why, because understanding the reasoning is what's going to help you on trickier variations of this question. So when you're using the Kafka connector for Snowflake, you basically get a choice in how much control you want. Default pipe mode is built for simplicity. You point the connector at your Kafka topic, and Snowflake automatically creates the target table and the snowpipe object for you. It even handles the mapping of your JSON fields into table columns without you lifting a finger. That's exactly what minimal setup means in this context. You're not writing DDL, you're not manually creating pipes. Snowflake just takes care of it. Now compare that to user-defined pipe mode, which is option D. That mode flips the script. You're the one creating the tables and pipes manually. It gives you way more flexibility. Maybe you want custom transformations, custom column names, whatever it is, but it absolutely is not minimal setup. It's the opposite, really. So if you saw minimal setup in the question and picked D, I get why, but that's actually testing the wrong concept. And the other two options, B and C, those are honestly a bit of a trap because they pull in concepts from a completely different ingestion method. External stages and the copy into command, those belong to batch file loading, not Kafka streaming ingestion. Kafka data doesn't sit in a stage waiting to be copied. It's continuously streaming in and Snowpipe handles it as it arrives. So if you ever see Kafka paired with stage or copy, that's usually a sign something's off in the answer choice. So what's the real takeaway here? When the exam describes a scenario and uses words like automatic, minimal effort, or out of the box, that's almost always pointing you toward default behavior, not a custom or manual configuration. Keep an eye out for that pattern. It'll save you on more than one question. All right, we're cruising along here. Let's hit question 4. And this one honestly catches a lot of people off guard, even people who've used Snowflake for a while. It's about warehouse defaults. Here's the scenario, and listen closely because there's some detail packed in here. A newly hired Snowflake engineer creates a warehouse using only the statement create warehouse devcore wh semicolon without specifying a warehouse size parameter. The engineer then navigates to Snowsite to verify the configuration. The engineer also recalls that Snowsite defaults differ from SQL defaults. So the question is, what warehouse size will the engineer see in Snowsite, and which creation method actually uses xlarge as its default? Here are your choices. Option A, the warehouse will show xlarge because all warehouses default to xlarge regardless of creation method. Option B, the warehouse will show xsmall, and xlarge is the default for Snowsite created warehouses only. Option C, the warehouse will show small because SQL creation defaults to small for compute efficiency. Option D, the warehouse will show medium because all warehouses default to medium regardless of creation method. Take your time on this one. This is the kind of question where people guess based on a vague memory instead of the actual documented behavior. So really think it through. All right, the correct answer is B. The warehouse will show xsmall, and xlarge is only the default for warehouses created through the Snowsite interface. Now you might be wondering, why does that even matter? Why would Snowflake have two different defaults depending on how you create the thing? Let's break that down together, because this is honestly a really practical, real-world gotcha. So here's what's happening. When you create a warehouse using plain SQL, the create warehouse command, and you don't explicitly set a size, Snowflake falls back to xsmall. That's the documented default for the SQL path. It's the smallest, cheapest compute option, which honestly makes sense as a safe default. You don't want someone accidentally spinning up a giant warehouse just because they forgot to type a size. But here's where it gets interesting. If that same engineer instead goes into Snowsite, the web interface, and clicks that nice little create warehouse button, the default size that gets pre-filled is xlarge, not xsmall. Xlarge. Two completely different starting points, depending purely on which door you walk through to create the warehouse. Now think about why this actually matters in the real world. Imagine you're building an automated deployment pipeline, maybe using Terraform, or some CI/CD process that runs SQL scripts to provision new environments. If your scripts use create warehouse without explicitly setting a size, you're going to get xsmall warehouses every time, which is usually fine, predictable, cheap. But if someone on your team is manually creating warehouses through Snowsite and just clicking through the defaults without paying attention, boom, they've just spun up an xlarge warehouse, and that's going to show up on your credit bill in a big way. That's a real cost story, not just a trivia fact. So the reason this question shows up on the exam is because Snowflake wants to make sure you, as someone managing a production account, understand these subtle but financially significant defaults. It's not enough to know Warehouses can be different sizes. You need to know what happens when nobody specifies a size at all, because in the real world, that happens constantly. All right, let's keep going. Question 5, and this one's a multi-select, so heads up, there could be more than one right answer here. This is also one of my favorite questions in the set because it's super practical for anyone doing real cost management in Snowflake. Here's the scenario. A Snowflake data engineer is analyzing warehouse efficiency using the load monitoring chart. The chart shows that the warehouse has been running for 2 weeks, but the total query load is consistently below 0.5 for most hours of each day. What actions should the engineer consider to reduce excessive credit usage? Here are your 5 options, and remember, this is multi-select, so more than one could apply. Option A, disable auto-resume to prevent the warehouse from starting automatically. Option B, enable auto-suspend with an aggressive low timeout value. Option C, decrease the warehouse size to reduce credits consumed per hour while query load is low. Option D, increase the warehouse size to reduce query duration and improve efficiency. Option E, decrease the min cluster count parameter for the multi-cluster warehouse. All right, pause it, think it through. Which of these actually makes sense if your warehouse is sitting there underutilized, burning credits for basically no reason? Okay, welcome back. Let's talk about this one because this is a really practical, real-world cost optimization scenario. And the correct answers here are B, C, and E. Let's go through each one because understanding the why here is honestly going to make you better at your actual job, not just better at the exam. So first, let's talk about what that load monitoring chart is actually telling us. A query load consistently below 0.5 means the warehouse is barely being used. It's like renting a giant moving truck to carry one box across town. You're paying for capacity you're not using. So option B, enabling auto-suspend with an aggressive low timeout. This makes a ton of sense. Auto-suspend means that when the warehouse sits idle for a certain period, Snowflake automatically pauses it and you stop getting billed for compute time. If your workload comes in bursts, query, then nothing, then query again, an aggressive timeout means you're not burning credits during all that dead air in between. Now, option C, decreasing the warehouse size. You might be wondering, wait, doesn't a bigger warehouse mean faster, more efficient queries? Well, sometimes, yes, but only if you actually need that horsepower. If your query load is consistently low, that tells us the warehouse already has more compute than it needs. Sizing it down means you pay a lower credit rate per hour. Yes, your queries might take a tiny bit longer, but if they were already comfortably fast on a bigger warehouse, that's basically wasted money. Right-sizing your warehouse to match actual demand is one of the single biggest cost levers in all of Snowflake. And then option E, decreasing the min cluster count parameter for a multi-cluster warehouse. So, quick refresher, multi-cluster warehouses can spin up additional clusters when concurrency demands spike, which is great for handling bursts of simultaneous queries. But there's a setting called min cluster score count that controls the minimum number of clusters that must always be running, even during quiet periods. If that minimum is set higher than it needs to be, you're paying to keep clusters alive that aren't actually being used. Lowering that minimum means fewer idle clusters sitting around burning credits when nobody needs them. Now let's talk about why D and A are wrong, because this is just as important. Option D says increase the warehouse size to reduce query duration. But hang on, if your load is already below 0.5, that means the warehouse isn't even being pushed hard. Making it bigger just increases your hourly credit rate without solving an actual performance problem. That's literally the opposite of what you want to do here. And option A, disabling auto-resume. Think about what that actually does. If you disable auto-resume, your warehouse won't automatically wake up when a query comes in. Someone would have to manually start it every single time before running a query. That's not a cost optimization. That's just added friction and a worse experience for your users without addressing the actual issue, which is idle compute time. So what's the big takeaway here? When you see a low query load on a monitoring chart, your brain should immediately think, suspend faster, size it down, and reduce the minimum cluster floor. Those three levers together are basically the holy trinity of Snowflake cost optimization. And honestly, if you remember nothing else from this video, remember those three. All right, let's shift gears completely because question 6 takes us into the security side of things, Tainen, and specifically into one of Snowflake's more advanced encryption features. This one's called Tri-Secret Secure, and if you haven't run into this term before, don't worry, we're going to break it all the way down. Here's the question. Which statement about Tri-Secret Secure is correct? Option A, it uses only customer-managed keys. Option B, it's available in all editions. Option C, it forms a composite master key. Option D, it encrypts data blocks directly. Take a moment here. Think about what you know about layered security and encryption key management in Snowflake. All right, the correct answer is C. Tri-Secret Secure forms a composite master key. Now, this part's super important, so let's really sit with it for a second because the name itself, Tri-Secret, is actually a huge clue if you think about it. Tri meaning three. So right away, you should be thinking, okay, there are three components involved here somehow. So here's how it actually works. Tri-Secret Secure combines three separate pieces: a Snowflake managed key, a customer managed key, often called a CMK, and your authentication credentials. Snowflake takes those three components and merges them into something called a composite master key. And here's the key detail that the exam loves to test. That composite master key doesn't directly encrypt your raw data. Instead, it wraps or protects the account master key, which sits one layer above your actual data encryption keys. So why does this layered structure even matter? Well, think about the security implications. Because the customer holds one of the three pieces, their own managed key, that means if the customer revokes or destroys their key, the master key can no longer be reconstructed. And without that, your account master key can't be unwrapped, which means your data effectively becomes unreadable. That's an incredibly powerful security control because it puts a literal kill switch in the customer's hands. If you ever need to immediately and permanently lock everyone out of your data, even Snowflake itself, you control that lever through your portion of the key. Now let's quickly knock out why the other answers are wrong because each one represents a really common misconception. Option A says it uses only customer managed keys. Nope. Remember, it's a combination of three things, not just one. If it were only customer managed, it wouldn't be called Tri-Secret, it'd just be customer key management. Option B says it's available in all editions. This is a big one to remember for the exam. Tri-Secret Secure is restricted to Business Critical Edition and above. It's not something you get on Standard or Enterprise. So anytime you see a question implying this feature is universally available, that's your signal something's off. And option D, encrypts data blocks directly. This misunderstands the entire layered architecture. The composite master key never touches your raw data directly. It protects the account master key, and then a whole separate chain of file keys actually handles the data level encryption. Tri-Secret Secure operates way up at the top of that hierarchy, not down at the data block level. So what does this really mean for you if you're studying for the exam? Whenever Tri-Secret Secure comes up, think three components: composite key, wraps the account master key, business critical, and above. If you can recall those four facts, you're basically set for any variation of this question they throw at you. All right, let's roll into question 7, and we're staying in the security zone here, but this time we're talking about authentication methods, which honestly is becoming a bigger and bigger topic on the newer versions of this exam. Here's the question. Which authentication method requires network policies as compensating controls? Option A, workload identity federation. Option B, key pair authentication. Option C, programmatic access tokens. Option D, single sign-on. All right, think this one through. Which of these credential types is the kind of thing that, if it leaked, could be reused from basically anywhere unless you lock it down? Okay, the answer is C, programmatic access tokens, often abbreviated as PATs. Let's break down why, because this is genuinely useful knowledge if you're working with automation, APIs, or service accounts in Snowflake. So picture what a programmatic access token actually is. It's a credential, essentially a string of characters that gets passed along with every single API request to prove who you are. Now here's the issue. Because that token has to be transmitted with each and every request, it becomes a juicy target if it ever gets exposed. Maybe it ends up in a log file by accident, maybe it gets checked into a code repository, maybe it's intercepted somehow. If a bad actor gets their hands on that token, they can potentially use it from anywhere in the world to access your Snowflake account, pretending to be you. So that's exactly why Snowflake requires what's called a compensating control here, specifically network policies. A network policy lets you restrict exactly which IP addresses or IP ranges are allowed to actually use that credential. So even if a token leaks, an attacker sitting outside your approved network range simply can't use it. The token alone isn't enough anymore. It also has to be coming from an allowed location. That's a really powerful extra layer of defense for a credential type that's inherently a bit risky just by its very nature. Now let's go through the other options. Workload identity federation. This is actually a newer, more modern approach where short-lived tokens get issued based on native cloud identity attestation. Because these tokens are short-lived and tied to verified identity providers, the exposure window is naturally much smaller, so it doesn't carry that same mandatory network policy requirement. Key pair authentication. And look, I want to be careful here because network policies are absolutely still a smart idea with key pair auth. They're just not mandatory the same way they are for PATs. The risk profile is different because key pair auth typically involves a private key that's harder to accidentally expose compared to a token sitting in a header on every API call. And single sign-on, option D, this one relies on your identity provider's own security controls. Think Okta, Azure AD, whatever your organization uses. The security responsibility there largely sits with that external identity system rather than with IP-based restrictions inside Snowflake itself. So what's the real-world lesson here? If you're an architect setting up service accounts or API integrations using programmatic access tokens, don't just create the token and call it done. Pair it with a network policy every single time. That's the kind of layered thinking Snowflake wants you to demonstrate, both on the exam and in your actual day-to-day work. All right, we're 2/3 of the way through. Let's keep this energy going. Question 8, and we're moving into data loading and staging, which honestly is one of the most foundational practical topics on the whole exam. If you're doing any kind of ETL or ELT work with Snowflake, this one's directly relevant to you. This one's also a multi-select, so listen carefully. Here's the question. In a Snowflake bulk loading process using copy into, which components are required for successful ingestion? Here are your 5 options. Option A, stage location. Option B, virtual warehouse. Option C, file format definition. Option D, query result set. Option E, storage integration. All right, take a moment. Think about what copy into actually needs to function. What's truly required versus what's just optional, depending on your setup. Okay, the correct answers here are A, B, and C. Stage location, virtual warehouse, and file format definition. Let's walk through why, because this question is really testing whether you understand the fundamental mechanics of how bulk loading actually works under the hood. So let's start with the stage, option A. A stage in Snowflake is basically a pointer, a location where your raw data files live before they get loaded into a table. It could be an internal stage, meaning it's storage managed inside Snowflake itself, or an external stage, pointing out to something like an S3 bucket or an Azure container. Here's the key thing. Copy into only reads from stages. It doesn't load data directly off your laptop or some random URL. Without a stage, Snowflake literally has no idea where to find your files. So that one's an obvious must-have. Now, option B, the virtual warehouse. This is the piece people sometimes forget about. But think about it logically. Somebody has to actually do the work of reading those files, parsing them, transforming the data, and inserting it into the target table. That's compute work. And in Snowflake, all compute work runs through a virtual warehouse. Without an active warehouse, copy into simply has no engine to execute the operation. It's a mandatory runtime dependency, full stop. And option C, file format definition. This one's all about how Snowflake actually interprets your raw files. Are they comma separated? Are they pipe delimited? Are they JSON? What's the character encoding? Is the file compressed? And if so, with what algorithm? Without a proper file format definition, Snowflake genuinely doesn't know how to correctly parse your data, and you're going to run into all kinds of mapping errors or garbled data in your target columns. So this is absolutely a required piece of the puzzle for accurate ingestion. Now let's talk about why D and E aren't required. Option D, query result set. And this one's a little bit of a trick because it sounds vaguely related to loading data. But a query result set is something you get back from running a select statement. It's not an input to copy into at all. Copy into is fundamentally about moving data from staged files into a table. It's not pulling from query outputs in its basic standard form. So that one's just unrelated. And option E, storage integration. Now, this is the trickiest one of the bunch because storage integration is genuinely useful and important, but only in a specific scenario. It provides secure credential-free authentication when you're connecting to an external cloud storage location like S3 or Azure Blob Storage. But if you're using an internal stage, you don't need it at all. So it's situational, not universally required, which is exactly why it's not one of our correct answers here. So what's the big picture takeaway? Think of warehouse, stage, and file format as the core ingestion triad. The three things you absolutely cannot run a successful copy into without. Storage integration is more like an accessory you bring along specifically when you're dealing with external cloud storage. Keep that distinction clear and you'll breeze through loading related questions on the exam. All right, now let's get into the two scenario-based questions because these are honestly the meatiest, most exam realistic questions in our whole set today. These are the kind of questions where Snowflake gives you an actual script or an actual diagram and expects you to reason through it like a real engineer would. So pay extra close attention here. Question 9, and this is all about continuous data protection, specifically time travel and fail-safe. Two concepts that sound similar but work really, really differently. Here's the scenario. A data engineer runs a script against a permanent table that normally inherits the account's default retention period of 1 day. The engineer lowers the retention period to 0 immediately before dropping the table, and then attempts to recover it 2 hours later. Based on the script and Snowflake's data protection lifecycle, what is the outcome of the final undrop statement? Now, picture the actual script running here, because the sequence really matters. First, there's a comment noting the account default retention is 1 day. Then the engineer runs use database sales scored DB. Then comes an alter table statement on sales.orders, setting the data retention time in days to 0. Right after that, there's a drop table statement on that same sales.orders table. And then 2 hours later, after realizing the mistake, the engineer runs undrop table sales.orders. Okay, here are your 4 answer options. Option A, undrop succeeds because the account level default of 1 day overrides the table level setting. Option B, undrop fails because time travel was disabled before the drop and the data may still briefly exist in failsafe, which is not user restorable. Option C, undrop fails permanently because drop tables can never be recovered in Snowflake under any circumstances. Option D, undrop succeeds because the alter table statement only affects future time travel queries, not the drop that follows immediately. All right, really sit with this one. Trace through the script line by line in your head. What actually happens to that table's recoverability the moment that alter table statement runs? Okay, let's talk through this because this is honestly one of the trickiest, most nuanced questions in the whole set, and the correct answer is B. Let's break that down together, step by step, because the sequencing here is everything. So here's the core thing you need to understand. Time travel retention isn't some abstract setting that only applies going forward in some delayed way. It takes effect immediately the moment you change it. So when the engineer runs that alter table statement setting retention to 0, and then immediately drops the table right after, that table no longer has any time travel window at all. 0 days means 0 days. There's no grace period. There's no buffer. The very next operation, the drop, happens against a table that already has no retention safety net. Now you might be wondering, okay, but doesn't Snowflake have some kind of backup beyond time travel? And yes, it does. That's failsafe. Failsafe is a separate, completely non-configurable 7-day period that automatically applies to permanent tables, but only on Enterprise Edition and above. Here's the catch though, and this is the part that's super important. Failsafe is not something you, the customer, can access or restore from directly. You can't run an undrop and pull data back from failsafe. If you genuinely need that emergency recovery, you have to open a case with Snowflake support and ask them to do it on the back end. It's purely a last resort disaster recovery mechanism, not a self-service tool. So when our engineer runs undrop table 2 hours later, that command fails because there's no time travel data left to restore from. The data might technically still be sitting in failsafe somewhere in Snowflake's internal systems, but undrop simply doesn't have access to that layer. That's exactly what option B is describing, and that's why it's correct. Now let's quickly go through why the other three don't hold up. Option A claims the account level default of 1 day overrides the table level setting, but that's backwards. Table level settings take precedence over the account default at the moment an operation occurs. The account default doesn't swoop in retroactively to save the day. Option C, saying recovery is impossible under any circumstances, that's actually overstating things, because failsafe could theoretically still provide emergency recovery through Snowflake support, even if undrop itself won't work. And option D, suggesting the alter table only affects future queries, not the very next drop. Nope, the setting change is immediate and applies right away, including to whatever operation comes directly after it. So what's the real-world lesson buried in this question? If you're ever doing maintenance work, scripting, or cleanup operations against tables, and you're tempted to lower retention temporarily for whatever reason, just be incredibly careful about the order of your operations. Lowering retention and then immediately dropping a table in the same script is basically removing your own safety net right before you need it. This is exactly the kind of subtle, sequence-dependent trap that the real COF-C03 exam loves to test, because it shows whether you actually understand the mechanics, not just the vocabulary. All right, let's move into our final question, question 10, and this one is all about query performance and micropartitions, paired with an actual visual diagram that you need to reason through. Here's the setup. Picture 6 micropartitions for an orders table, each one labeled with the minimum and maximum value range of the order date column, stored right there in its metadata header. A query filters on order date between March 10th, 2026 and March 15th, 2026. And here's an important detail. The table has never had an explicit clustering key defined on it. Based on the partition ranges shown in that diagram, the question asks, how many micropartitions must Snowflake actually scan to answer this query, and why? Now let me walk you through what those 6 partitions actually look like, because you really need this picture in your head to reason through the answer. Partition 1 covers January 1st through January 31st. Partition 2 covers February 1st through February 28th. Partition 3 covers March 1st through March 12th. Partition 4 covers March 8th through March 20th. Notice that one overlaps a bit with Partition 3. Partition 5 covers March 21st through April 5th. And Partition 6 covers April 6th through April 30th. So here are your 4 answer choices. Option A, all 6 micropartitions, because pruning requires an explicit cluster by key to be defined on the table. Option B, only 2 micropartitions, P3 and P4, because their min-max date ranges are the only ones that overlap the query's filter range. Option C, only one micropartition, because Snowflake always scans the most recently written partition first and stops once it finds a match. Option D, 4 micropartitions, P2 through P5, because Snowflake scans a buffer of adjacent partitions around the matching range for safety. Okay, take a moment here, and I really mean it. Actually compare those date ranges against the query filter of March 10th through March 15th. Which partitions could possibly contain a matching row and which ones obviously can't? All right, let's work through this together. And the correct answer is B. Only 2 micropartitions, P3 and P4, need to be scanned. Now let's really understand the mechanism here, because this concept called pruning is honestly one of the coolest performance features in all of Snowflake. And once you get it, you'll never forget it. So here's what's happening behind the scenes. Every single time Snowflake writes data into a micropartition, it automatically stores metadata about that partition, including the minimum and maximum values for every column. This happens completely automatically. You don't have to ask for it. You don't have to configure anything special. So for our orders table here, each of those 6 partitions has a stored min and max for the order date column, exactly like the diagram showed us. Now, when a query comes in with a filter, in our case, order date between March 10th and March 15th, Snowflake's optimizer looks at that filter and compares it against the min-max metadata of every single partition before it even reads any actual data. If a partition's range falls completely outside the filter window, Snowflake just skips it entirely. It doesn't even open the file. That's called pruning, and it's a huge reason why Snowflake performs so well even on enormous tables. So let's walk through our 6 partitions one by one with that filter in mind. Partition 1, January 1st through 31st, way outside our March range, pruned, skip it. Partition 2, February 1st through 28th, also completely outside, pruned, skip it. Partition 3, March 1st through 12th. Now this one overlaps because March 10th through 12th falls right inside that range. So this one has to be scanned. Partition 4, March 8th through 20th. This one also overlaps our filter window because March 10th through 15th sits right inside that range too. So this one gets scanned as well. Partition 5, March 21st through April 5th. Starts after our filter window ends on the 15th, so it's pruned, skip it. And partition 6, April 6th through 30th, way outside, pruned, skip it. So when you add it all up, only partitions 3 and 4 actually overlap our query's date range. That means Snowflake only needs to physically read and scan 2 out of the 6 total partitions. The other 4 get eliminated before any actual data reading happens, just based on that lightweight metadata check. That's exactly what option B is describing, and that's why it's the right answer. Now here's a really important nuance buried in this question, and it's the part that catches a lot of people off guard. Notice that the question specifically says this table has never had an explicit clustering key defined, and yet pruning still works perfectly fine. Why? Because pruning isn't something that only kicks in once you manually define a clustering key. Snowflake automatically tracks min-max metadata for every micropartition regardless of clustering. That's exactly why option A is wrong. It claims pruning requires an explicit cluster by key, but that's a really common misconception. Clustering keys don't enable pruning from scratch. What they actually do is improve the efficiency of pruning that's already happening automatically. By keeping similar data values physically closer together, inside fewer, narrower range partitions, especially as a table grows huge or gets reorganized frequently over time. And let's quickly knock out C and D as well. Option C, the idea that Snowflake scans the most recently written partition first and stops at the first match, that's just not how the engine works at all. There's no concept of most recent partition first scanning behavior. Pruning decisions are based purely on metadata range overlap, completely independent of when the partition happened to be written. And option D, suggesting Snowflake scans a buffer of adjacent partitions for safety, there's no such buffering behavior either. Snowflake only scans partitions where the metadata actually indicates a potential overlap, nothing more, nothing less. So what's the bigger lesson here for the exam, and honestly for your real-world Snowflake usage too? Selective filters on well-distributed columns can dramatically reduce the amount of data scanned, even without you doing any manual tuning whatsoever, simply because of this automatic metadata-based pruning. And if you do define a clustering key down the road on a massive, frequently updated table, you're not turning pruning on, you're making the pruning that already exists even sharper and more efficient. That distinction, enables versus improves, is exactly the kind of subtle wording the real exam loves to test you on. Okay, take a breath because we just covered a lot of ground together. Let's do a quick lightning recap before we wrap things up, because repetition is honestly one of the best ways to lock this stuff into your memory before exam day. Question 1 taught us that replication groups can absolutely be modified for content and scheduling, but they can never be converted into failover groups. Question 2 showed us that centralized storage is the real engine behind Snowflake's ability to scale compute independently without ever moving data around. Question 3 reminded us that default pipe mode is your go-to when you want Snowflake to handle Kafka table and pipe creation automatically with minimal setup. Question 4 taught us that surprising little gotcha, SQL creation defaults to extra small, but Snowsite defaults to extra large, and that distinction genuinely matters for cost control. Question 5 gave us our 3 big cost optimization levers for underutilized warehouses: suspend faster, size down, and lower that minimum cluster count. Question 6 walked us through Try-Secret Secure, that composite master key built from 3 components, exclusive to Business Critical Edition and above. Question 7 showed us why programmatic access tokens specifically require network policies as a compensating control, because of how easily they can be transmitted and potentially exposed. Question 8 nailed down the real ingestion triad for copy into your stage, your warehouse, and your file format, with storage integration only coming into play for external cloud storage scenarios. And then our 2 big scenario questions, 9 and 10, really tested whether you can trace through an actual script to understand time travel and fail-safe timing, and whether you can read partition metadata to understand exactly how Snowflake's pruning engine decides what to scan and what to skip. Honestly, if you walked through all 10 of these with me and you're feeling more confident than when you started, that's exactly what this video was meant to do. The SnowPro core exam isn't really about memorizing definitions in isolation. It's about understanding how all these pieces actually connect together and play out in real, practical scenarios, exactly like the ones we just worked through. So here's what I want you to do next. Go back, rewatch the scenario-based questions 9 and 10 one more time, because those scripts and diagrams are exactly the style of thinking you need for the real exam. Practice tracing through sequences of operations in your head, slowly, deliberately, the way we just did together. And if this video actually helped you, do me a favor, drop a comment letting me know which question challenged you the most. Hit that like button and subscribe if you haven't already, because we've got a lot more of these practice sessions coming your way as you work toward passing the SnowPro core certification. Thanks so much for sticking with me through this whole video. I really appreciate you being here. Good luck with your studying. You've absolutely got this, and I will see you in the very next one.